Welcome to the lecture 6 of the course Basics of Fluorescence Spectroscopy. So, till last class we were discussing about the absorption spectroscopy, and in the last class we were discussing about the effect of solvent on the absorption spectra. It means that how the color of a substance may change by changing the solvent, right. So, by changing the solvent means changing the solvent property, and where we are discussing about the changing the polarity of the solvent. And in this case we have discussed about as shown here the phenomena of negative solvatochromism, right, phenomena of negative solvatochromism. In this case what we have seen that there will be a blue shift in absorption spectra by increasing the polarity of the medium for a molecule whose, right, what is the property of the molecule? The property of the molecule is for that molecule where the ground state dipole moment mu g is greater than excited state dipole moment mu e, right. So, let us see that what happen if the situation is just reverse, right. What I want to say is that in the case of excited state dipole moment is more than the ground state dipole moment, then what will be the situation. So, here my condition is that mu g is less than mu e, right. So, as usual let me take my molecule represented by this ellipsoid, right, over here. So, this is the ground state and this is the excited state, and in this case as I said that ground state dipole moment is less than excited state dipole moment. Let me define this as 2 positive charge over here and 2 negative charge over here and 4 positive charges over here and 4 negative charges over here, right. So, now let me put this molecule in a solvent of polarity P1, and which obviously is going to stabilize both the ground state and excited state, and let us say the stabilization is like this. So, from the solvent point of view, right. So, this is the solvent dipoles, and over here will be something like this. So, the absorption is instantaneous again. So, that takes only 1 femtosecond or less than a femtosecond. So, when you excite this molecule from ground state to the excited state by light h nu 1, let us say for example, which is equal to h c by lambda 1. So, the electronic transition is instantaneous. So, solvent will remain as it is because it takes time to move around, and let us define the energy here as G 1, the ground state energy with polarity 1, and this energy is E 1. Now, I change the solvent from polarity P 1 to polarity P 2. Let us see what will happen. Here is my polarity P 2, so that P 2 is greater than P 1, right. So, P 2 is greater than P 1. In this case that same molecule 2 positive charge, right. So, same dipole moment over here, and here as the polarity P 2 is greater than P 1, it will be more solvated, right. So, let me represent it by 4 solvent dipoles over here. Right. So, then again I am going to excite this molecule from ground state to the excited state, and here is my excited state dipole moment is more. than the ground state dipole moment, but as the excitation is instantaneous, I am not going to have a different solvent structure around this molecule. So, solvent structure will remain as it is in the ground state. So, let us say this energy over here is G2 and energy over here is E2, and this excitation energy is H nu 2, which is equal to H C by lambda 2, right. So, now I can plot the relative intensities of G1 E1 and G2 E2. Let us say this is the level of G1 and this is the level of E1, G1 E1, right. So, this is for the polarity P1, and when the polarity has increased, P2 is greater than P1, then what we can see is that the energy will be minimized, right. So, the energy will be minimized. So, this is my G2. However, this excited state dipole moment, right, is more, right. So, energy minimization of the E2 compared to E1 will be much more compared to the ground state, right. So, here this energy minimization will be more than ground state. So, here it will be E2, right. So, you see here this energy difference is H C by lambda 1, and in this case this is H C by lambda 2, and this energy is more than this energy. That means, lambda 2 is less than lambda 1, sorry, lambda 2 is more than lambda 1, lambda 2 is greater than lambda 1. That means, in this case, as you can see that by increasing the polarity, right, by increasing the polarity, the absorption spectra is shifted towards the lower energy, shifted towards the lower energy means longer wavelength. So, I can write here absorption maxima shifts towards lower energy or higher wavelength. This means the red shift in the absorption spectra, red shift in the absorption spectrum, right, by increasing the polarity of the medium, right. So, this is referred to as the positive sulfatochromism. And for the positive sulfatochromism, what I saw that mu g is less than mu e. And if, as you remember, for the negative sulfatochromism, what we saw, mu g is greater than mu e for negative sulfatochromism. Okay, so this is about the effect of solvent on the absorption spectra, and based on this, right. So, one can generate polarity scale what has been done by Reichert. So, this is very well known polarity scale which is known as ETN polarity scale. So, what I want to say is that is the following: as the absorption spectra, right, changes right, depending on the polarity of the medium. So, if I have a molecule where the change or the shift in the absorption spectra is reasonably high, then by referring the absorption spectra of that particular molecule, I can comment on the polarity of the medium. Right. We know the polarity of water is very high, polarity of cyclohexane is very low, and so on and so forth. Now, if you have a solvent with unknown polarity, you can simply dissolve that particular dye and measure the absorption spectra, and if it resembles with the absorption spectra of water, then you can say the polarity is near about water. If it resembles to the absorption spectra of dioxane, then you can say okay, the polarity of that unknown solvent is like dioxane, and so on and so forth. So, with this one can actually formulate a polarity scale, and which has been done by the Reichert, right. So, this is known as Reichert's polarity scale. Reichert's polarity scale or ET30 scale, ETN scale, all these are polarity scale, right. I will explain these things. So, what Reichert did, he took a dye, right, whose structure is something like this. Right. So, you see this molecule is polar, right. It has a large dipole moment in the ground state, but when excited, this molecule become radical. That means the dipole moment decreased. So, in this particular case, it is the case of mu g is greater than mu e. So, if I dissolve this molecule, right, in different solvents, so what I expect? I expect that as the polarity will increase, there will be a blue shift in the emission maxima. So, let us see what are these values. So, for this particular dye, right, if I write the solvent over here, solvent, right, then absorption maxima, right, like this. Okay. So, for octane is a non-polar, right. Octane, this value what he observed is 919 nanometer. So, when he changed this octane to benzene, the value he observed is 833 nanometer. When he changed it to propanol, he observed it as 564 nanometer, and in case of methanol, this is 516 nanometer, and in case of water, it is 453 nanometer. Right. So, I can simply plot, right, this different solvent versus absorption maxima, and then for a unknown solvent I can find this absorption maxima and can comment about the polarity of the unknown solvent, whether it is like octane or it's benzene or propanol, right. We can comment on that. However, we can do one step ahead and find out the molar electronic transition energy, right. So, molar electronic transition energy, right, denoted as ET of this particular dye we can calculate. So, molar electronic transition energy is defined as that how much energy is required for this electronic transition for 1 mole of the substance, right. So, that is nothing but Hc by lambda max into Avogadro number, right. Hc divided by lambda max for a particular solvent into Avogadro number, isn't it? Okay. So, this I can write all the value 6.626 10 to the power minus 34 joule second. C is 3 10 to the power 8 meter per second. Lambda max is lambda max in nanometer or in meter. So, just I write lambda max, right, lambda max, and then this Avogadro number 6.023 10 to the power 23 per mole, right, into 6.023 10 to the power 23 per mole. So, if we solve this, so see this second inverse second cancel out. So, this will going to be joule and this meter here is also lambda max is in the meter, right. So, if I want to put this in the nanometer, so better I write lambda max into 10 to the power 9 if it is represented in nanometer. So, then I will put 10 to the power 9 in the meter. So, then meter will cancel, right. So, now if we put all these values over here, this will going to be, now if I convert the joule to calorie, so then this will going to be 28610 divided by lambda max in nanometer, right, in nanometer kilocalorie per mole. Okay. So, I can simply divide, right, this lambda max to this 28610 kilocalorie per mole, and then I can write over here the corresponding values, right. So, here I will write ET is generally denoted as ET30 for this dye, generally ET as I written, but it generally represented as ET30. That number 30 is nothing but this dye number, because when Reichers did this study, he used varieties number of dyes, right, and this particular dye found out to be the most useful one by Reichert, and in his original paper the number of this dye is happens to be number 30 dye. So, it is written as ET30 value of this particular dye, right. Whenever I write ET30, that means it is this particular dye molecule. So, if I now convert, I will get the different values of ET30 from this equation, right. So, for this one, this will going to be 31.1 and this one is 34.3, this is 50.7, this is 55.4 and this is 63.1. It means that this particular solvent octane has a corresponding value of 31.1, right. This for this particular dye, this is molar transition energy, right, ET30 value. So, However, as you can see here, these values starts from 31 for a very non-polar solvent, and for the most polar solvent this value is 63.1. So, this is actually not that good scaling, right. The scale should start from 0 and 1 or 100 and 0 and like that, then this scale looks much better, right. So, but then what he did, he just normalized. So, instead of ET30, what he used a normalized ET30, right. So, let me write over here normalized ET30 scale, which is denoted by ETN, right. So, this is defined as ET of solvent of your choice, right, minus ET of most non-polar one, right, the non-polar one, most non-polar one divided by ET of most polar one minus ET of most non-polar one. So, he took the most polar solvent as water. So, here what he took is this as water and non-polar as TMS, right. So, this TMS, this is TMS. So, these value are constant values, right. So, this value, these are the constant. So, when the solvent is water, this value is nothing but 1, right. When the solvent is water, this value is nothing but 1, and when this solvent is TMS, then this value is going to be 0. That is it. So, now I convert this ET30 scale to a normalized scale of polarity, which is known as ETN scale, right. So, now if I just simply write the corresponding value of ETN over here. So, the octane becomes 0.012, right, 0.012, water become 1.000, right, and then methanol is 0.762, propanol is 0.671 and benzene is 0.111, right. So, what we can see is that we got a solvent polarity scale, ETN scale, and this ETN scale is a widely used solvent polarity scale, because it contains all the interaction, because the shift in the absorption spectra is a resultant of all possible interaction between the solvent and the molecule, that sulfotochromic dye, in this case the Reichert 30 dye. Okay. So, if somebody says that the polarity of this particular solvent is something like 0.01, then it is evident that this solvent is non-polar solvent. If it is like 0.8, 0.9, then this is a polar solvent, right. Okay. So, now let us move to this topic, the fate of excited molecule. Like till now what we have seen is that we are exciting this molecule from one state to the other state, right, by absorption of radiation, right, that we have seen. So, and that gives me the absorption spectra, right. So, depending on that from ground state to the first excited state or second excited state, the absorption spectra change, and if we scan the wavelength and plot the absorbance, what we are going to get is the absorption spectra. So, by the absorption of this electromagnetic radiation or light, the molecule goes from the ground state to the excited state. Now, the question is, after you promote the molecule from ground electronic state to the excited state, that is abide by the Frank-Condon principle, right, that we have already discussed. So, what is the fate of this molecule? The molecule will remain in the excited state forever, or it will undergo some kind of deactivation process, and ultimately it will come back to the ground state, right. So, that is the topic right now what we are going to discuss, and I see the time is up. So, we will going to discuss in the next class. Thank you very much.